Welcome all. Good afternoon, everyone. Welcome to our next session, which is on numerical simulation of additive manufacturing processes in Simulfrac. We have our speaker, Mr. Anand Padmanabhan. He is currently working with Solace India Technologies as a senior technical lead. Mr. Anand Padmanabhan, mechanical engineer with over 12 years of experience in the CAA and structural simulation domain. He holds a bachelor degree in mechanical engineering from VTU University, Karnataka. He has built deep expertise in supporting, training and implementing advanced simulation tools, particularly within Hexagon MSC softwares, suites including Simulfrac, MSC, Nastran and MSC Mark. Throughout his career, he has worked closely with cross-functional teams from design, production, tooling and engineering to establish robust CAE process and deliver technical upskilling. He has successfully led many number of proof of concept projects, delivered specialized corporate training sessions and provided hands-on technical support to prominent Indian clients in the automotive, aerospace, defense and manufacturing sectors. His strengths lies in non-linear analysis, customer training engagements and aligning simulation capabilities with the real-world engineering challenges. With this brief introduction, I would like to welcome Mr. Anand Padmanabhan to take over a session. Thank you.
Thank you everybody for this opportunity to be standing in front of you and delivering a talk on numerical simulation of additive manufacturing processes using Simulfrac. So Simulfrac is basically a FEA tool. Like in the morning sessions we had several talks on additive manufacturing, DD processors and as well as LBF processors. So how we can use numerical simulations to help us achieve our simulation techniques in additive manufacturing using Simulfrac. That is what the talk we are going to have for today. So just a brief overview, like the corporate profile of where I come from. Basically, we are from Solace India Technologies Private Limited, and this organization was founded in 1992. Earlier, it was known as CSM Software Private Limited, and from there, Solace, which is a Japanese company, had acquired this particular CSM Software Private Limited, and hence from there on, we have been known as Solace India Technologies Private Limited. And for our talking about our services and solutions, we offer product design solutions as well as testing and validation solutions. Design solutions, we are a leading partner with Dassault Systems in India, basically for CAD and PLM technology distribution. And coming to the CAE front, in the technology distribution, we are a top level partner of Hexagon or the MSC software products. So this particular tool, Simulfrac, which we are going to talk about, comes under the CAE distribution technology, which is under Hexagon. Okay. And we also have engineering services divisions in our corporate office at Bangalore, which is offshore CAD as well as CAE service from India to customers around the world. And we engage with MNC's global design operations as a sharing engineering center. So we have the services aspect as well as the technical support aspect in the corporate world. Okay. So this is basically basic overview. And our main customers like include government companies, mainly the aerospace companies like HAL, NAL, and several government companies, as well as automotive companies, academia, as well as engineering services companies also. So this is a basic overview of our organization. And coming into Solace India, we are actually 30-year-old customer-centric organization with about 1,000 plus customers, and we offer a reliable solution in digital product design, validation, and manufacturing. And when I talk about the design and manufacturing or the validation, we are official business partners with Hexagon, VA Grade, and companies like Torre, and for CAD coming to Dassault Systems and Systems. Okay. So this is basically our introduction to our team, which is Their corporate office is in Bangalore, and we are spread across the country in various cities. And coming to the solution that we offer, like coming to the global portfolio of products, right from materials to systems. Okay. So when we talk about systems, or it is basically the starting point in the materials section. How we model our materials, how we characterize our materials. Then comes fabrication, then comes part modeling, assembly, and system-related analysis. So when we talk about materials, we have softwares like Digimat, Material Center, which are mainly used for material characterizations of metallic components or composites and things like that. And whether you are involved in the virtual testing of these materials, where you want to create your own materials, test them virtually, and then analyze them using the FEA tools, we can do it using the Digimat software. And coming to fabrication is mainly on Digimat, additive or simulfact additive, or it can be simulfact forming, which is mainly the fabrication technologies that we have. Then the part related aspects like modeling as well as geometry cleanup and things like that can be done using Apex or Market. Okay. So then as comes to assembly solutions, assembly means comes to the welding or joining technologies, we have again the simulfact tool for that. Okay. And then system related things. System related things is your FEA analysis. Like you can use CFD analysis or structural analysis and so on and so forth. We have SE flow for CFD analysis and Nastran pattern for structural analysis. And people must be interested in multi-body dynamics, that is addressed by Atom software, and also acoustic simulations, which are addressed by Acton software. So these are the various tools that we have. So now, since our point of interest is on simulfact, that is mainly used for additive manufacturing solutions. So that is our topic for the day. So I'll be just giving you an overview of what is simulfact, and then we will proceed to the specific applications of simulfact where it can be used for additive manufacturing, whether it can be direct energy deposition techniques or power bed fusion techniques. Okay. So simulfact basically stands for simulating manufacturing. So simulating manufacturing, or we can say it's a manufacturing division of MSc software. So MSc software is a part of Hexagon company. So they are under they are doing the development for this particular tool. Okay. So simulfact supports metal-based manufacturing process. It can be welding or any kind of forming analysis for additive manufacturing. And the technology that is being used behind simulfact is nothing but the mark and the diagram solvers. So these solvers are multiphysics solvers, which are being there in the market from a long time. And if you take mark, it's a very multiphysics nonlinear implicit code, which is mainly working behind the simulfact to solve our multiphysics problems. Okay. Then we have diagram solvers also, which can be used in forging simulations or hot forging simulations and things like that, where it is an explicit solver. Okay. So this is an introduction to the simulfact, like how it is there in the picture. So based on the type of analysis or the vertical that we have simulfact forming and simulfact additive and simulfact welding. Simulfact forming can solve all the forming related manufacturing processes. It can be in the cold forming domain, hot forging domain, sheet metal forming, ring rolling, and so on and so forth. Whichever is like applicable to your requirement in forming aspects, we can solve it using simulfact forming vertical. And another vertical is simulfact additive. Additive is mainly targeting the powder bed fusion or PBF process. It can be the DMLS process or SLS process or EBM process. Several things can be addressed. Whichever is powder bed fusion techniques can be addressed using simulfact additive. Okay. Then we have the welding. So simulfact welding can address simulations pertaining to arc welding, laser beam welding, and the topic for our today is like metal deposition techniques. which can be all addressed by the SimulFact welding module. Okay. So we shall get into that step by step. Like for example, whichever I was mentioning, like for example, if you are doing the powder bed fusion techniques, it can be SLM or selective laser melting, or direct metal laser sintering process like EMLS process, or EBM process, electron beam welding. We can use this in fact additive software. Okay. And deposition techniques, laser based, arc based, or electron beam based, whether it can be powder or wire based, it can be addressed using SimulFact welding software. Okay. The deposition techniques are nothing but our DD techniques, which I was mentioning in the morning sessions. All those things can be solved using SimulFact welding model. Okay. So, if plastics are involved or composite materials are involved, we have a module called DigiMat which can solve something like FDM or FF kind of simulations. It can be solved using the DigiMat plastics. Okay. So these are all the modules or different types of tools that we have to solve different kinds of problems. Okay. So coming to our next slide, that is, I will give a brief overview. Yeah. Coming to the next one. So whenever we are solving or whenever we are performing metal, additive manufacturing solution, or it can be a PVF process or a DD process, there are many challenges that comes into the picture actually. Okay. And those challenges, whether the simulation by doing a virtual simulation can be addressed or not. Or we might be doing in real life applications to arrive at a result. We might do several trial and error using the machine or using the technology, and we go back and then do the rework and things like that using physical prototyping or physical testing. So how we can reduce these kind of physical testing, because physical testing anywhere we cannot avoid it. But the number of tests or the number of trials that we do can be addressed by keeping the solution or simulation as a back-end solution actually. So this will reduce our effort as well as your time and effort as well as money which goes into the testing as well as the physical prototyping. So how simulation can be helpful? For example, it can help us in assessing or finding out distortions in part dimensions which is going out of tolerance, or suppose if you are doing a PVF or a powder bed fusion technologies, whether the deformations are coming more, such that if there is collision with your equator plate and there is a machine jam and then there is a wastage of time as well as material. So these kind of things can be analyzed using the simulation techniques, using SimulFact additive or welding. And another things would be residual stresses. So all these technologies that are there, whatever is running behind is a FEM or FEA code, finite element analysis code, which will help you to analyze part or part distortion or residual stresses, which are the reasons for part failures, cracks, okay, as well as collisions with the equator plate in case of powder bed fusions, or it can be delamination in case of DED process. These kind of things can be analyzed with respect to results such as residual stresses or distortions that comes into the picture. And due to these kind of defects, our parts fails in the during the build when you are manufacturing the part, or it can fail after manufacturing part when it is part is performing in the service actually. Okay, these kind of things can happen actually. So how we can overcome these kind of situations is what we are going to study. Then another aspects will be like quality defects and whether the studying or density of the parts, whether the parts are more dense or whether there are some the density of the part is less such that the part is not able to perform in the real life scenario, as well as implications. Implication in the sense whatever we are discussed, like iterative trial and error required. and high cost in time and resources actually. So these are the reasons why we have to use a simulation. For example, if you see a titanium bicycle frame section, which is manufactured using a powder bed fusion method actually. Okay. So during this method, since this involves localized heating, whenever we are heating a material or a powder with a localized heat source, there are a lot of chances that it will go out of distortion or it can cause crack like this actually. Okay. So these kind of products are manufactured by using support structures here. Whenever we are using a powder diffusion methods, we have the part as well as there are support structures. So the support structures are comparatively very less denser compared to the part which we are trying to manufacture. So this can cause some issues like cracking, or it can cause some failure, or you can see the parts going out of tolerances when there is a rapid heating and cooling of the parts which are getting manufactured layer by layer. So these kind of things, how we can address? We can address it up to a certain extent by doing a simulation. Okay. So AM workflow or additive manufacturing workflow to date, something like you have a design with you, okay, and then suppose it might be an automotive or aerospace kind of component which we have designed, and then you want that design to come into manufacturing, and then you want to use it for your application. So what we will do is we will design the component, we will try to build the component actually. Okay, it can be using the LBF or the DD methods. We try to build the components, then we try to inspect the components where like for any failure or any defects in the product actually. So once you have identified defects or something like a part going out of tolerance, we need to repeat this process again. We need to either change your design or modify your building strategy. You have to modify your scanning strategy, or we have to modify our heat input strategy, or heat input parameters we have to modify. So this is something like a very cyclic process. We have to do many trial and error to achieve a successful component which is able to perform in the real life scenario. So this takes a lot of trial and error. So what if we can include something like you can say an AM simulation in between in between your design and your build, actual build. We can create an AM simulation, and we can detect these kind of defects in your simulation, in your virtual simulation, such that you can save all these building and inspection, all these things efforts can be reduced. Okay, that is our main idea of doing a simulation. So from this simulation, first like if you are able to find out these things using a virtual simulation, we can always go back to our CAD design. We can modify the design, or we can modify the build parameters, and then we can analyze it. We can arrive at a particular less or you can say product, a build with less errors, which can be finally send it back to the build, and then we can continue our design or inspection process. So this will reduce our cycle in which we are trying, investing in our trial and error issues or testing or things like that. So there the simulation comes into picture. So this is where we are going to use the simulation as an added or a complementary solution to reduce the efforts in manufacturing. So in simulation, if we talk about, there are several scales by which we can do the simulation actually. Okay. So it depends on the type of simulation that you are doing, or the kind of results that you want, or it can be something like the computational effort that you are looking for, and things like that. Okay. So here we have three. They have divided this into three main simulation types. One is the macro scale simulation, meso scale simulation, and then we have the micro scale simulation. Okay. So macro scale simulation, when I talk about macro scale simulation, it is nothing but a purely mechanical simulation where we are trying to capture something called inherent strain, which comes in the components when the component gets printed actually. So these inherent strains can be purely mechanical, and it can be material specific, machine specific aspect actually. Okay, when we are talking about the macro scale. So why we use macro scale is it is very less time consuming process. It can we can easily do experiments to capture the material behavior easily to make your physical print, and as well as it delivers the distortion and stresses actually. Okay. So if our aim is to study the distortion and stresses on the part, we can use the macro level simulations actually, which can be easily solved using the additive as well as the welding technologies. So next level of simulation is the mesoscale. Mesoscale means element layer analyzed step by step in a hatching or segment wise actually. Okay. So this is something like we are capturing thermal, mechanical and thermomechanical coupled aspects in the simulation. So if your aim is to study the thermal aspects in the simulation also, then we can use the mesoscale simulation, and it will be able to deliver us thermal history as well as mechanical results like distortion, stresses, strains. All these aspects can be solved using the mesoscale method. And one more mesoscale, the application of mesoscale is most of the PDF process that we solve are solved using the mesoscale approach. Because as you know, the PVF process is a very time consuming process where the powder has to be melted layer by layer using the scanning strategy as well as the slicing software. So each layer will be something like in microns, varying from, it can be from 30 microns to 50 microns of material has to be laid layer by layer, and we have to build the part actually. So when that is involved, it is very difficult to in a computationally when we talk about the computational effort, it is very difficult to analyze it using the microscale method. Okay. So that's why we use the mesoscale method, which is a faster solution, but at the same time we can study the thermal behavior of your body, and due to the thermal behavior connected with the distortion, stresses, as well as the the temperature, the melting behavior of the the powder or the material that we are trying to use, we can study it using the mesoscale. Then the final thing would be the microscale. Microscale is the finest level that as far as the finite element method is concerned, where we are using a moving heat source. So this will exactly capture how your scanning strategy is there on the laser, how whether it is a whatever strategy is there, you can model it, capturing the G codes from your robot or from your machine. You can capture it and study the moving heat source. The heat source will move along with the time. So this is a completely thermomechanically, methodologically coupled solution where we can study thermal history and as well as the microstructural details also. Okay. So mostly this method we won't prefer here because this will take more time to analyze. When we are going for a component level or part level analysis, we mainly use mesoscale as well as a microscale. And to make this more, you can say by using the less computational efforts, as well as we have to arrive at a more closer results to our reality. We use many methods to arrive at those solutions. So that we will be discussing in the coming slide. So when we talk about the macro scale or the mechanical approach, we generally have different techniques to analyze these kind of components actually. So whether we if we talk about LBF process or the power bed fusion processes, whenever we take a power bed fusion process machine like EOS machine or something like a manufacturing kind of scenario, so there we will have different kinds of aspects which we are going into consideration actually. So there can be laser based parameters that we have to take care. Powder quality, how powder quality is there, okay, and the machine, whether it is a new machine or whether it is used machine. So all these aspects will cause difference in the the part distortions or the behavior how the part when it is printed actually. So when you, for example, if you take a new machine like a Dios machine or a drum machine, and when we start printing the part, we we have captured some, let's say, some distortions. So after some time, when we change the powder or when we change the material parameters and when we print it using the same machine, then again the distortions might be varying. Your machine is same, but again the results are different. So how can that be possible? Okay. So that kind of aspects can be related to the the quality of the powder, the power input. So after the machine gets more and more used, the efficiency of the machine might be coming down. So due to that, there can be difference in the results actually. So to take care of that, we use something like an approach in SimFact additive, that is the powder bed fusion method, where we print physical samples actually. Okay. So each and every time when we are doing a print, we will build physical samples, something like these. These are called the cantilever samples. So they are like standard samples which we try to print it on the machine before we print the actual part. So why do we print these samples is like to understand the behavior of the component or behavior of the material actually. So here in this case it can be a titanium alloy or inconel alloys, or it can be something like a managing steel. So each and every time when we print, we should get the behavior of the material same actually. Okay. So what we do here is we try to capture something called plastic strains, thermal strains, creep strains, or phase transformation strains. So all these strains combined are known as inherent strains. Okay. So inherent strains are specifically, it is very, you can say, a particular material will be having a particular inherent strain. If you take titanium, it will have a particular inherent strain, and if you take something like another material or inconel material, it will have a specific inherent strain. So we are trying to capture those strains, and then we are trying to build the component inside the software. We try to build the part in the machine. We try to compare you can say the displacement which is coming in our simulation as which is coming in the part. Okay. So after we do that, what we do is we do something called as a calibration study. We will study whether our simulation is matching with our part build actually. Okay. So there are some techniques in the software to you can say calibrate your displacements or your strains which is coming in the simulation and the part, and then we extract the inherent strains from the software actually. These inherent strains will be put in your actual build part for analyzing the actual component. Okay. So from this, what we are trying to do here is in the simulation we can't capture all your machine parameters. There can be n number of parameters when you are actually printing a part or using a particular machine. So how we can reduce all those parameters for our analysis so that we can match our experimental as well as simulation. That is what we are trying to do here in the calibration procedure. So after you calibrate, you can do the analysis. So analysis, as I said, it can be the meso level, which is the mechanical analysis, or if you want to study the thermal analysis, where you want to capture the thermal behavior of the component, layer by layer, we can able to capture it. So what does it enable us to predict? We can predict distortion, stress, which is coming on the part, supports or the base plates, okay, as well as peak temperatures, whether the peak temperatures are in the simulation or in the whether our laser parameters are giving us the right peak temperatures to melt the powder, or the proper fusion of the powder is happening, or the wire is happening. These kind of aspects can be studied here using the heat flux and peak temperatures. Likewise, we can use the thermomechanical approach to study the part behavior. So here we have a part which is getting built here. So here we can see the layer by layer. This is a PVF process actually, which is solved using SimFact additive. Okay. So here you can see we're building the part, how we can say it works on a technology like activating the element layer technology. So where each and every layer is activated based on the type of input that we are trying to give here. Okay. So it can be something like, from this analysis we can study the distortion, stress, strain results which can be displaced, and we can study deviation. So most of the parts which are manufactured in using the powder bed fusion technique or the DD techniques, the main challenge is addressing the distortions actually, how we can address the distortions as we had seen in the earlier talk given by Ajay. So how simulations can be used to reduce these kind of distortions? We can study using the part techniques. And in addition to that, the part might be subjected to something like heat treatment, because initially when you build the part can have residual stresses which are highly responsible for cracks or failure of components during the cycle, during the operating cycles of the part. So heat treatment processes can relieve the stresses. So we have methods to relieve the relieve the stress using heat treatment techniques. Whether it can be something like stress relief heat treatment, or it can be specific heat treatment technologies which we want to simulate, something like a benching or TAP, something like technologies with respect to these temperature over time kind of scenarios. We can simulate it using the Simulfact welding as Simulfact heat treatment knowledge. So you can see here how the equivalent stress buildup will happen after the part is getting printed, and how after the heat treatment is done, how the stresses can be relieved from the part. So which will improve the material characteristics of the component. Okay. So for this we have several creep laws, etc., which can be input into the software. Based on this creep laws, it will calculate the stress relief heat treatment techniques. And then we have support removal. So if you are doing a LPF process, we might be, after building the part, we may have to separate the part from the base plate using the cutting or the removal of the support structures from the component edge. So whether that can be simulated or not, yes, it can be simulated using the cutting and removal support structures, where it will essentially, as far as the FEM is concerned, it will change the stiffness of the structure. So whenever the component is attached to the base plate, the result that we get is entirely different when we cut it from the base plate, because the stiffness is released from the component and the end distortions will be completely different when we are doing the component, or when we are manufacturing the component and when we are measuring the distortions with the base plate. So sometimes we use the base plate, we do the heat treatment along with the base plate, and then we take the measurements after cutting. So several methods can impart several differences in the behavior of the components. So those kind of things can be addressed using the Simulfact modules. And then we can also study hot isostatic pressing heat process, which are most commonly used in powder-based manufacturing process, where we provide the time as well as the pressure over time data, and we can study the relative density of your build before as well as after doing the densification. Okay. So it uses some densification formulas to arrive at the relative density of your part. So all these things can be used to optimize your AM process change. So mainly it involves additive manufacturing, or whether we are doing a heat treatment, then we are cutting and removing the base plate, or doing a heat process. Everything can be analyzed virtually in a additive or in the Simulfact additive environment. So how it helps is, for example, we have to do these different scenarios in a physical way. For example, let's say we are having a part like this. We have a few support structures which are modeled here, and we are trying to print it actually. Then we find that there are some distortions coming on the part. Okay. So we are trying to, let's say, we are telling, okay, the support structures are more. We want to optimize the support structures such that we want to get less amount of distortion at that particular part actually. So how we can use this simulation? We can use the simulation to do support structure optimization, to optimize the amount of support structures or the areas in where the support structures are necessary to reduce these kind of defects or these kind of issues which can come in the reliability. So those kind of support structure optimization as well as part optimization can be done using the SimulFact additive tool. So here I chose, for example, distortion as well as stresses which are studied for build, during the build, during the heat treatment, during the cutting as well as removing the support structures. So and we do the each and every application or each and every process, it will give us the resultant result in a real-time scenario. Despite the best efforts, distortion may be still out of tolerance. So despite doing all these things, we might still face issues. So how we can overcome those issues? So next one would be something like, so you might be facing, so you might be hearing something called compensation techniques. So even if you, I can say, use all your parameters right, and whether you are doing all the scanning strategy or any strategies and the material aspects you have taken care, then also at the end of the print you may get some deviations or you can say distortions at the end of the print. Okay. So this can happen during the physical print. For example, if you see here, this is your initial component which with the initial build and with the initial support section. So after printing, the component will distort, okay, and then it will be it will give us some distorted geometry, which is when you measure it, you will see that the part is going out of the tolerance section. Okay. So what we do is we do a simulation on this, and we do something called as a compensation. We compensate the geometry in such a way that when we print the part, we should get the part within the tolerance section. Okay, so that is known as a distortion compensation. So there are right now in simulation softwares we are having specific methods to address these distortions by using automatic distortion compensation to take care of these kind of errors that these kind of issues that can come in the part build. Okay. So these are all automatic options are available in the software where we need to do certain number of iterations to arrive at a part which will help us to print with the least distortion. So this shows a snapshot of how the simulation happens in the software and what kind of components that which can be printed using the PPF process. So this is an example for an impeller plate which is printed using the powder bed fusion technology. Can be something like a titanium or infrared kind of materials. So here we can study the distortions. Here we can study the temperature distribution as well as the effective stresses when you are building up. And also you can say see the stresses that is getting involved during the different aspects of build. So now we are after build we are doing the cutting operation, and then the support removal will happen. So at the end of we will get the end where we can study the stresses which are coming on the component. So this is coming to a case study. Like this is a green team wheel carrier case study. So here we have the component. So here this was a study done in collaboration with Renisho and SimulFact, the green team in Germany. So here we have a formula student electric team, University of Stuttgart. So they collaborated and made a study on this particular aspect. So here we have the component here, and it is something like a suspension, upright bearing carrier. So this to get this part printed. So here you can see the component. To print it using the additive manufacturing technology. So whether this would be feasible or not. So if you take an automobile or vehicle like this, whether the component will survive with respect to the loads which are coming on the vehicle or not, we have to study. That too by using a powder bed fusion technique. So here the material used was TiAl6B4, the titanium powder, and the tool steel was the base plate for this particular material. I mean for this particular build actually. And it had around 5 lakh elements, and then around 82 layers of elements actually. And thickness of the support is 0.3 mm. Okay. So these are the inputs that we need as a whenever we are considering FEA perspective. We need to discretize the model and we need to make the necessary element count so that we can study the behavior of the component when we are building the part. So on your screen here we can see the component getting built, and then you can see it is getting built, and then the base plate is removed, the support structure removal is done, and then the further processing is done. So there, after building the part, you can see here the measurement correlations were done, which requires specific predictions actually. So this shows the component, and then there are certain locations where the point 1, 2, 3, you can see several locations where after the building the part or after the building the part in the tool in the software, we are trying to match it with the real life print actually. Okay. So there you can see the scale displacements, which is showing in the simulation as well as in the experiment. So we are getting a good amount of correlation between the experiment and the simulation. So this was done for different stages, like build stage, then base plate removal stage, support removal stage. So all these things aspects, different studies are done with respect to residual stresses as well as displacements. We can do it. And heat treatment was done to reduce the, of course, the heat treatment has to be done because building any component using the laser-based techniques will involve residual stresses in the component. So how to relieve those things? We have to use a heat treatment cycle to remove the residual stresses actually. So that is being shown here after explaining how the residual stresses are removed. Then one more aspect is cracks, which can it can be something like a crack which is forming between the support structure and the component. So that can be predicted using the software. We can use it by simulation can predict cracking basically at local locations like these, or we can identify high risk locations and conduct virtual trial to reduce the risk. So after building the print, if you are finding these kind of issues, again you have to go back and then modify your input parameters actually. So that will involve again the cycling process where we have to use the material to build the component as well as the time which is required to build these kind of components. So that can be very much reduced if we are doing a simulation. We are arriving at some study where we can identify such issues well in advance actually. Okay. Then another aspect would be, even if you have built a part, like morning we had seen, we are doing something like optimization studies to make the components lightweight in nature. Okay, lightweight in the sense like using additive technologies where the conventional part, which is shown something like this, whether it can be optimized with respect to the weight such that we can remove the material from the component, as well as we have to maintain the performance of the component or the strength of the component, which has to perform in a way such that it has to perform in a similar way as the real component or the conventional component. So for that we do the topology optimization studies, where we use the loads and constraints on the component to study the material where and all the material is not required, it can be removed, and then we build the part, we study the part, and then finally we decide whether we can use this particular part for the actual component actually. Okay. So for this several studies can be done. For example, using the topology optimization, we can make multiple design concepts like design variants. Okay. So the topology optimization tool will give you a number of design variants. So in these different variants, if you observe, there are slight variations in the design in each and every design actually. So which is the most apt or which is the most you can say, suitable design which you can use. It has to be studied using the virtual manufacturing as well as the further FEA analysis. Actually. It can be stress analysis or fatigue analysis. Several analysis has to be done to arrive at a solution. So that can be done further to the printing or the virtual printing analysis. So in this virtual printing analysis, when we are getting these different variants, which is the best variant we can pick. Some variant might give you like less weight, but it may not be feasible to use that aesthetic wise, or it can be part performance wise. It cannot be used in the real life scenario. So we cannot always judge based on the weight reduction or things like that. We have to consider many other aspects, like we have to do multiple FE analysis, whether it can be static analysis or dynamic analysis we have to perform, and then we need to arrive at a particular design. Okay. So here the topology optimization will help us to optimize the component with respect to material topology based optimization algorithm. So here it shows we use a tool called Apex Generative Design. There are several tools in the market, and one of them is Apex Generative Design, where we use the initial CAD design and we use the loads, the design constraints and the loads to arrive at the design by using the material removal, using generative design kind of techniques. So here you can see the component where the material is removed wherever it is necessary, and the material is retained wherever there is a design constraints. It can be both locations, constrained locations, or it can be the component phases where we want to retain. Those parts it will retain, and then it will create a generative design based on that. So this particular, it will give you a smooth geometry which is ready to print actually. So you can send this as an STL file or a CAD file. You can export this file and then feed it into your additive manufacturing simulation to further continue from the continue into the additive manufacturing simulation using the AI or the laser based technique. So here it shows the component which is used for the AM build simulation and the cutting process. So here you can see that particular animation shown over here. So after this we study the distortion which is coming on this part. We will see whether this is able to print the part. Sometimes while printing this part we will try to fade. Like for example, if the distortions, local distortions are high, the machine will, the recoder or the machine will come into a halt where if the recoder jam happens at a particular layer, then we have to discard the entire part and then we have to start building the part again. So this physically doing it is a very risky task, so we use the simulation to check whether these kind of issues can happen in the real life scenario or not. Okay. Then we have another aspect is like optimization of build process. Like when we are trying to build a part, we suppose this is a base plate of the machine. Sometimes machine comes in different sizes, like it can be 280. Like if you take the US machine, it will come up to 400 by 400 mm base plate dimensions. That can be the maximum dimension the machine has. So whether a part can be printed using that kind of setup or not, we can use it using whether we can use a single part or whether we can build multiple parts on the base plate. So if you take a big component like this, the base plate will be we can only build a single component on the base plate actually. And we can study on different aspects like build. You can say what you can do is the orientation actually. So which is the best orientation for building the component. So here if you see he has kept a different orientation, and here if you see it is something like a different orientation actually. So in whichever orientation if you print, you will get minimum distortion or minimum failure with respect to the part. So this can be, to do this in a machine, you will have to do, physically build this and again build this and then compare it. Instead of that, we can virtually simulate it and we can study that, which will make us our efforts much lesser. Okay. So that is this particular tool is comes along with the SimFact additive tool, where with respect to different inputs, it can be build height, your orientation, it will generate the best orientation for your model based on different inputs we are trying to give it. So here is the support structure optimization. So when we are talking about PBO process, we have again the support structures which has to be generated along with the part. So if you are trying to print the part, the support structures gets printed along with the part actually. So wherever we need the support structures, or which locations we don't want the support structures, so we can use support structure optimization to reduce or add support structure based on the geometry, based on the loads which are coming on the component actually. So this can be simulated and we can use it for your actual print. So after arriving at this optimized support structures on the part, we can send this part to the actual printing. Okay. So here you have the component which is printed, and then it is put to use for the particular the way. So this is something like what we are talking about the PBO. So when we talk about the direct energy deposition or the laser based or arc based technique for DD components. So how we can use Numerical welding for that. Okay. So Numerical welding also is a specific tool. So it can solve welding kind of scenarios where we have arc welding, laser based, electron beam based, or you can say direct energy deposition, or any of these several aspects can be simulated. Recently, several years before, since nowadays we are having the additive technologies into pictures. So development started happening in this area, that is the direct energy deposition. And Numerical has introduced this particular direct energy deposition module inside the Numerical welding engine. So why welding is because we use the same techniques to build the components. It can be laser based heat source or the arc based heat sources. Whatever the heat sources, we are using the welding techniques to build the components layer by layer. So that's why it is introduced in the Numerical welding module. So here what we generally do is here everyone must be aware. Like we build the CAD, then we build the DD path planning using the path planning tools, or from the machine we take up the the path scenarios, and then we create the G code and we try to build the part actually. Okay. So building this part directly, as you know, it is very challenging for arriving at a particular part which is having specific the behavior or with respect to distortion, stresses, or it can be something like the microstructural details. Everything can be an aspect when we are trying to build the component directly. So whether any simulation can come in between this, and whether we can make use of the simulation software to reduce our efforts in these when we are doing metal deposition techniques actually, or metal deposition methods. That is the main criteria. So why do we need a simulation? Because we are already doing the physical trials. We are already doing that in our day-to-day life. Why do we need a simulation actually? How does it help us? Like, if you are doing the physical printout, you are saying that, like, if you take the design and process like a confidence on a graph, you can see that we are very uncertain how the things would end up actually when we are doing a physical build. Okay, we have to do n number of physical trials to arrive at a simulation, or to arrive at a specific output, which can be time consuming, which can be expensive, because we have to use a lot of material to print these kind of components, and it requires physical parts to be printed, to be physical. We need to do many tryouts to arrive at some solutions, as well as limited design changes. So since we have to print this part each and every time, it will involve a lot of effort actually. So that will limit our design changes, as well as the freedom to choose the design, or whether we have to change something again, we have to do the things again all over again. So this kind of things can be addressed using the simulation. So DD manufacturing is a complex and can be very difficult to predict. So that is why the simulation or such kind of FEA simulation can be used, or it can be complemented along with your physical printing, mainly because the DD quality can be impacted mainly by the thermal management strategy. Like for example, if you are using the heat source to melt the component or melt the wire or powder, whether the heat, the laser parameters or these laser speed, scan speed, everything is appropriate or not. Okay, if it is not appropriate, it can cause overheating or underheating, and based on that, it can affect our end result, which can lead to distortions or many manufacturing issues with respect to the quality of the component which is getting produced. So that is why this can be very challenging. It can be impacted by this thermal history, and it can be impacted by residual stresses. We saw in the earlier slides how the residual stresses build up when we build the component actually, as well as base plate deformation. So whenever we are trying to build a component, you must be knowing when we have a substrate or a base plate on which we are trying to build the component actually. And as we build the component, continuously we are heating and cooling. Okay. So this continuous heating and cooling involves lot of material characteristics which gets changed during the formation, during the part formation as well as during the base plate deformation. So this involves lot of if the base plate gets deformed too much, that will also affect the end part productivity. So these kind of things, whether we can address it or not, we can address it using simulation up to a certain extent, where we can use these particular tools to analyze these things. Additional potential issues, like for example, undesirable like microstructure, cracking, and fatigue failure in service. So these can all happens after the component might be built, and when we are trying, when the component tries to perform, it may undergo some failure or fatigue in the service. So all these are potential issues that can be come across when we are doing a DD or a direct energy deposition methods. So this results, what happens is, what we do is, we have these all issues. What we tend to address these issues, we often use physical trials. Excess physical trials, scrap or rework becomes more actually. Okay, many things gets failed, and then you have to again start from scratch one or step one. So that involves a lot of scrap and rework that happens in the scenarios in a build service. So virtual tryout. Virtual tryout is something like which is shown here. So here we have the base plate on which the part is getting manufactured. So the heat source can be laser based or wire based, or it can be laser based technique or additive or arc based techniques. We can use either of the techniques to build the component or simulate the parts like this. So from this we predict DDD process outcome like thermal, distortion, stress and strains actually. Okay, and then we understand the outcome before any physical trial. So we try to, for example, if we try to build the part and we measure it using some measurement, we find the part is going out of tolerance. So how do we do that? Like what parameters we can modify to bring the part into tolerance actually? It can be something like a scanning strategy that you are trying to use, or something like a G-code modification that you are trying to make, that can be studied using the DD or the manufacturing, simulating the manufacturing process. So here we can study many things like power settings. For example, the power that goes into the simulation or the printing, clamping or fixing strategy. So wherever you are clamping these components, so how the clamping strategy is there, based on that, the distortions also might vary in real life. Okay. So then deposition sequences, how we are trying to sequence the deposit using the the metal or wire based techniques actually. Interpass temperature, whether using any interpass cooling or heating in between the passes. So that also will matter. Okay. Then purposefully building the parts out of nominal and many other things which we can study. So all these things, if you are doing it on a physical tryout, it will take a lot of effort. We can always use these kind of tools to optimize your settings actually, and then we can build the part, we can compare it with your physical build, we can come at a conclusion whether this is okay or not. Okay. And this particular thing you have seen in the morning slide. So here we are trying to the repair approach using the DED techniques. So here the process oriented approach. So we can see the you can say it will support all kinds of you can say criteria, whether it can be something like a deposition, able to handle large models, whether the model is large or whether it is having multi-axis deposition, and we have whether it is using a process-oriented user interface on the shop floor. Or these things, what we try to do here is we don't have a limitation as such in terms of the size of components which we can print or the complexity of the component which we are trying to print here. So this will give us a process-oriented approach. It can be something like supports all DED principles. Whether you are using a laser, arc, EB, wire or powder, we can use in all types of DED disciplines. And we can use the direct G codes from your machines or your setup. You can directly import it into the simulation and you can start printing the component. So when I am showing a demo of the software, I will show you how to work on the tool. So this shows an animation where we are having the additive manufacturing distortion simulation where the part is getting printed. So here we can see the heat source which is traveling to the component, and here we have the simulation for that particular tool. So we can see the heat source moving, and there are several methods to model the heat source. Like we can use the moving heat source, or whether we can also use the thermal cycle methods to model the heat source actually. And what all we can study stress, distortions, as well as you can say strains and displacements on the components when we are trying to build it. So this shows for different heights when the part is getting built. So at the end of this thing, we can see the stresses which are developing on the part when the part is getting built. So here we have a sample which is getting printed on the base plate. So here we have the convex side and the concave side, and then we have the dimensions on which it is getting printed. So 30 layer with 18 mm of total height is what the dimensions are there, which is mentioned over here. So after printing, we are trying to they have validated this for the deformations which is coming on the component in the experiment as well as the simulation. So this is a comparison study. This is like a research paper is available. If you require, we can share it for your further information actually. And then this shows the simulation on the part, which shows the after printing what are the distortions which are coming. Something like if it is lifting from the base plate, or if it is having something like outward bending deformation is happening when we are trying to build the part actually. So whenever the part is getting built after a certain height, it has started to distort. So this shows a simulation versus a 3D scan of the component, where we can make a comparison of the deformations, out of plane deformations, which is coming in the simulation as well as the 3D scan component. So we can see a similar kind of behavior. So validation is done for particular square geometry with 3D scans. So here we can see the part getting printed inside the software, and we get the result from here. And we are also actually printing the component on the base plate. We are getting the scanned data, 3D scan from the part. We are comparing the 3D scan with the simulated data. Okay. And then we have this can be done within the Simufact additive, where we have the distortion compensation tool, where we can do a shape comparison between the simulation and scan data. So after doing the simulation, whether your simulation is matching with your real print, real life print, you can make a comparison study. But you can get the scan data get it as a STL file, we can import it in the Simufab welding software. We can simulate the the part in the Simufab. We can compare the two parts and we can see how much of deviation is coming between the simulation and the scan data. So ideally we should be getting a close correlation between the actual build and then the simulation. So here one more thing is for DED, most of the tools where we face the challenges in getting the laser scan path or the scanning path. Okay, that is a very difficult path. Like earlier FEA codes were defining these paths manually by defining the path, defining the distance, or getting inside the tool, and then according to the coordinate systems we were trying to define the path in the tool, and then we were trying to import it. So right now the tool is the Simufab can readily import the G code directly into the tool, where it will readily read the the laser scan path, and you can see the build directions, the scanning path directions, as well as the strategy, as well as even the input, like power input and things like that. We can directly import it into the tool actually. So we don't have to spend time in these kind of scenarios where we have to define the scanning path in our analysis actually. So we can readily import the G code, and we can define the layers, and then we can start simulating the problem. Okay, so this will help the users to reduce the time they are spending in pre-processing. Okay. Then transient solution. So as we have the scan paths and the input here directly, we can define our read source. It can be laser based as it is shown here, or it can be an arc based, or the Goldak model which we use generally for the arc weld arc welding thing, or it can be a cylindrical laser beam which is used as a heat source. So we can model this using the Simufab welding, and we can start using it actually. Okay. Then we simulate it actually. So this shows the simulation. It has taken the G codes and it has taken the heat input parameters from the inputs as an input, and it will build the component. And another thing would be element set. So each and every layer that you are printing, we have to give a set of elements. Since it is at the end of the day we have a finite element simulation, so we need to have a certain number of elements at each and every layer of your build actually. Okay. So generally we use the finite element codes to generate the finite element mesh. So here in the FX, as hexagon, we are using the FX tool to generate the finite element mesh. We can also use the other meshing tools like HyperMesh, ANSA, many of the popular finite element codes that are there in the market. We can use those to create the mesh, and then we can automatically assign the elements to each and every layer that we are having in the deposit. Okay. So that can be decided by the user, or software has certain tools to decide in each layer how many layers of element we can take. That will happen based on the heat input geometry that we are having, as well as the parameters that we are having. Okay. According to that, it will automatically take the sets, element sets in your model. And also we don't have to worry about the contact related things, because earlier in normal softwares or FEA codes, we are generating each layer and we are trying to import it, and we are trying to define the you can say the path. So here we can what we can do is we can mesh the entire component as a single component like this. We can mesh the entire component, we can readily import the entire component, and inside the tool itself we can segregate the paths based on our layers based on our requirements. Okay. So here it shows the scanning path which is taken from the G code. So this is a sufficiently, like for example, this shows a very somewhat something like a larger model. In this larger model also we can try to capture the scan strategy, and we are trying to build the component edge. So they have solved even models with over 2 km of build length without grouping the layers. G code contains over 80K single linear movements actually. So it is not, the size of your model is not a constraint, but computational efforts can be a constraint. So you may need to have larger machines to solve these huge problems, because FEA code at the end of it requires computational efforts to solve these kind of problems. So this shows a nose cone model. I think this morning we have seen this similar kind of model. So the simulation happens like this. So here we have the laser blown powder DD. So it took something like a 48 hours of solver time, this particular model. And we are using the, you can say the laser based heat source to, to simulate this particular component. So it has, there are several ways to simulate this. We can use the, if you see the both the animations here, you can identify like how the the animation is there actually, how the heat elements are getting heated up. So here you can see a whole circle is getting heated up, but here you can see a parts of this is getting heated up actually. So this particular thing that we have several simulation techniques. For example, if you have to build this part, it will take a lot of time to simulate this. You see like this 48-hour simulation time. So to reduce this, we have certain methods, like we don't have to use an entire moving heat source. We also have thermal cycle methods, and then this kind of reduction methods where we can readily simulate using simplified techniques to reduce our calculation or solver time. So this can be done using the simulation. This is called as ATC method or thermal cycle method, which will reduce the simulation efforts which is there for the components. So next we can see here there is a repair operation actually. So morning we had seen how they are using DD for repair. So if we have the model which means we need to be repaired, we can readily bring it, and we can define our scan paths. We can see the make a thermal study, or we can make a thermomechanical study how the metal deposit which is happening here can impart bring the considerable deformations or any kind of issues in the part when we are trying to repair the part actually. So these kind of repair studies also can be addressed using the SUMUFACT welding module, where we can use the DD techniques to do that. So this also can be addressed using simulation. So the next one is like, for example, here if you see here, fundamental studies for simple geometries. So here you can see a study which is being done for a simple, like you can say a square or something like a rectangular pattern which is built on the base plate. So at the end of the simulation, we can see some high stresses which are there in the base plate, base of the component which is attached to the base plate. So there is high stresses coming there, also high strains are also coming there. Okay. So whenever this is happening, what we can infer or what we can arrive is, like when you build the part in a real scenario, something like this, there can be chances of delamination. So delamination can happen from the base plate with the part. So this can be well addressed. Like for example, before building the part, if you are trying to get this kind of study, you will come to know that okay, this kind of scenario or scanning strategy can cause this kind of stress or maybe delamination in the part. So according to that, we can change your laser parameters or input parameters to avoid these kind of things in the real printing. Okay. So this has there is a comparison study with this is with respect to the temperature and the height or the temperature and the thermal cycle. At a particular point, we have captured the temperature, and then it is several cycles are captured here. So it is they have shown that it is correlating with the simulation and the experiment. Okay. May not slight deviations might be there, but at least we can get the behavior in a proper way compared to simulation and experiment. Then another study like a distortion, like for example X distortion. After you go on building the part and then you pull down, due to shrinkage effects, there will be distortions like this actually, which will come normally in the DD processes. So how we can simulate that using the simulation and how they are correlated for the displacement in the positive X as well as the negative X. If you see the coordinate system here, okay, so this is the positive X and this will be the negative. Okay, so that they have made some comparisons. Next important thing would be your heat source, how we are going to model like heat input and boundary conditions calibrated on a single track. So we can make these kind of studies where we have the after doing the welding, we can take the micrograph, weld micrograph, and we can study the heat source with respect to the weld micrograph as well as the simulation. So this will come as a weld monitor in the, we can extract this data as a weld monitor in the simulation, where this shows the penetration, weld penetration in the simulation, and this shows the weld penetration in the actual component actually, or can say actual welding. So this will also help us in defining or calibrating our heat source. So at the end of the day, we need to get a part printed in the simulation which is close to our real life printing. So we try to calibrate the heat source with respect to the experiment as well as the simulation in such a way that at the end of the day we are trying to match it closely to our experiments. So this kind of thermal studies or thermal calibration study can be done in the SUMOFAC welding software, where we are trying to study the melt pool characteristics, or by using the simulation as well as by using the measurements which is coming from the experiments. So advanced thermal cycle is one technique where we can use this method to reduce our simulation time. For example, if you are trying to build a very larger component, mostly in the DED techniques, why DED is used is to build large components which are not possible in the powder bed, the laser based LBF process actually. Because LBF process is, first of all, it is something like a laser based, and also it has limitation with respect to the powder and the size of the component by which we can build. Normally the maximum base plate dimensions of a PBF or a we can say powder based machines will come up to 400 by 400. So beyond that, if we have components, we have to look at using DED approach. So for building the part in DED approach, for simulation wise, it is very challenging because of the size of the components. So having a small moving heat source, when we are trying to model this, to run this, it will take a lot of time. So there are some simplification techniques like advanced thermal cycle, where it will simulate your entire, you can say, a larger length of your deposit at a particular time, so that it will reduce the time which is used for simulating the entire component. So this will take much lesser time for you to analyze this. It may not be as I can say accurate as the moving heat source model, but up to, you can say, close relation to your moving heat sources, but it will reduce your computational effort actually. So this shows a comparison of the full transient. Full transient is a moving heat source model, which is exactly simulating your laser based or arc based simulation as you are doing it in the you can say DED process. So thermal cycle method, you can always use the thermal cycle method to reduce the computation time. But you can see the heat is the layer that is getting heated up. Here this is a moving heat source method, but here the entire layer is getting heated up. So this will take 40 hours to simulate, but this will take only 4 hours. so that time reduction you can do. Then this is also one more advanced thermal cycle method where they are using increasing the size of the the weld length so that we can get the results in a lesser amount of time. So if you ask me, this is the most accurate method, but the challenge is to simulate the component. Like it will take more amount of time to simulate it. And another showing the thing. So here we have the rear component which we saw earlier. So that is showing the simulation like this. And we have on the other part we are using the advanced thermal cycle method. So we can give different factors to this. If you give 50 and if you take 200, it will solve much faster. But it depends on the time and effort that we need to analyze this. So here there is a DED modeling correlation which is done for a component here. So we have component, and from there we have the component and the base plate. We have the G code which is there here, and definition of the heat source parameters. So if you see here, I am having the here we are having a golden heat source, okay, and then we are using the modeling in Apex. We are importing the component and the base plate in welding. We are importing the G code which we are having from external source. We are importing, we are defining the heat source parameters, and we are evaluating the results. So here there is a study which this is the real study, and this is the you can see the component which we have in the simulation. So there we are having different locations at which we are trying to extract the thermal history of the component. So the thermal correlations at different positions, position number 2, 6 and 9, which we will see it in the previous slide. So here we have different positions at which we are trying to track the history of the component actually. So here we can see a time versus temperature graph here. So we have the simulation data as well as the experimental data which shows the correlation. So again, here we can see the weld micrograph. Okay. So in the weld micrograph, we can see the substrate which is there on which we are depositing the material. Okay. So here, what we do in Sunopac is we try to model this using our CAD.
The dwell time before between the layers.
Yeah.
It's possible to improve the dwell time.
Yes.
Between each layer.
Yes. We can. Yes.
And over practically what we are going to do physically.
Yes.
If we compare it with other methods, how easily we can.
Yes, that is the idea. Like for example, if you are doing a pharmaceutical study, you might be unsure that how to use what is the best scanning strategy, whether it will cause any issues with your brain. That can be, if you do a simulation, you will come to know it prior to printing it. Then you can modify the strategy. You can start with it. Yes, yes, yes. Like we can do some iterations, some comparative studies, like modify, trial and error method we can modify, and we can study like that.
After the deposition, is it possible to study the mechanical properties of the wall? Example, is it possible to study the tensile strength of the wall?
We can study tensile strength, but for that we would prefer to do a multi-phase material, and then either we can create a weld, and then we can take those results and we can do a tensile study. But to capture that hardness and all in a correct manner, we may have to add some more material data, like multi-phase, data actually, like CCT diagrams and DDT. So that will give a phase-wise strength. So if you use a normal material, it may not capture that correct data. We can do, but our results might vary from the realized. We are doing a full testing. based on the weld strength only it will give the forces, right? So if you model the material correctly, we can do the pull test. That is possible in 3D.
Can we do phase analysis?
Which one?
Phase analysis.
Phase analysis can be done, yes. But our material data should be having the phase data, either the continuous cooling diagrams or the time temperature diagrams. Normally we work along with JMacro software. So if you are having JMacro software, you can generate the material, multi-phase material, we can use it readily in multi-phase.
Its output can be taken as input to the
Yes.